let's do some more problems that involve the ideal gas equation. So let's say I have a gas in a container, and the current pressure, so let's say that the pressure is 3 atmospheres. 3 atmospheres. And let's say that the volume of the container, the volume is, I don't know, 9 liters. 9 liters. 9 liters. Now, what will the pressure become if my volume goes from 9 liters to 3 liters? To 3 liters. So from the first ideal gas equation video, you can kind of have the intuition that you have a bunch of, and we're holding, and this is important, we're holding the temperature constant, and that's an important thing to realize. So in our very original intuition behind the ideal gas equation, we said, look, if we have a certain number of particles with a certain amount of kinetic energy, and we were to, they are exerting a certain pressure on their container, and if we were to make the container smaller, we have the same number of particles, n doesn't change, the average kinetic energy doesn't change, so they're just going to bump into the walls more. So that when we make the volume smaller, when the volume goes up, the pressure should go. When the volume goes down, the pressure should go up. So let's see if we can calculate the exact number. So we can take our ideal gas equation. Pressure times volume is equal to nRT. Now, do the number of particles change when I did this situation when I shrunk the volume? No, we have the same number of particles. I'm just shrinking the container. So n is n. R doesn't change. That's just a constant. And then the temperature doesn't change. So my old pressure times volume is going to be equal to nRT. And my new pressure times volume, so let me call this P1 and V1, and then P2 is this, and we want to, sorry, that's V2. Oh, no. So V2 is this, and we're trying to figure out P2. P2 is what? Well, we know that P1 times V1 is equal to nRT. And we also know that since temperature and the number of moles of our gas stay constant, that P2 times V2 is equal to nRT. And since they both equal the same thing, we can say that the pressure times the volume, as long as the temperature is held constant, will be a constant. So P1 times V1 is going to equal P2 times V2. So what was P1? P1, our initial pressure was 3 atmospheres. 3 atmospheres. So we have 3 atmospheres times 9 liters is equal to our new pressure times 3 liters. And if we divide both sides of this equation by 3, we get, what do we get? 3 liters cancel out. We're left with 9 atmospheres. 9 atmospheres. 9 atmospheres. And that should make sense. When you decrease the volume by 2/3, or when you make the volume 1/3 of your original volume, then your pressure increases by a factor of 3. So this went to times 3, and this went by times 1/3. And that's a useful thing to know in general. If temperature is held constant, that pressure times volume are going to be a constant. Now, you can take that even further. If we look at PV equals nRT, PV equal to nRT, the two things that we know don't change in the vast majority of exercises we do is the number of molecules we're dealing with, and obviously R isn't going to change. So if we divide both sides of this by T, we get PV over T is equal to nR. Or you could say it's equal to a constant. This is going to be a constant number for any system where we're not changing the number of molecules in the container. So if we're changing the pressure, so if initially we start with pressure 1, volume 1, and some temperature 1, that's going to be equal to this constant. And if we change any of them, if we go back to pressure 2, volume 2, temperature 2, they should still be equal to this constant. So they equal each other. So for example, let's say I start off with a pressure of, let me do it with 1 atmosphere. and I have let's say I have a volume of 2. I'll switch units here just to do things differently. 2 meters cubed, and let's say our temperature is 7. Let's say it's 27 degrees Celsius. Well, and I just wrote Celsius because I want you to always remember you have to convert to Kelvin. So 27 degrees plus 273 will get us exactly to 300 Kelvin. And let's say that our new temperature is, well, actually, let's figure out what the new temperature is going to be. Let's say our new pressure is 2 atmospheres. 2 atmospheres. The pressure is increased. Let's say we make the container smaller. So 1 meter cubed. So the container has been decreased by half, and the pressure is doubled by half. So you could guess. You know, we've made the pressure higher. The container. Actually, no, that's not it. Let me make the container even. Let me make the container even smaller. Let me make it. Actually, no. Let me make the pressure even larger. Let me make the pressure into 5 atmospheres. 5 atmospheres. And now we want to know what the second temperature is. And we've set up our equation. And so we have 2 over 300 atmosphere meter cubes per Kelvin is equal to 5 over T2, our new temperature. And then we have, what do we have? We have 1500, right? 1500 is equal to 2T2. Divide both sides by 2. You have T2 is equal to 750 degrees Kelvin. Which makes sense, right? We increased the pressure so much and we decreased the volume at the same time that the temperature just had to go up. Or if you thought of it the other way, maybe we increased the temperature and that's what drove the pressure to be so much higher, given, especially that since we decreased the volume. I guess the best way to think about it is this pressure went up so much, it went up by a factor of 5, went from 1 atmosphere to 5 atmospheres, because on one level we shrunk the volume by a factor of 1/2. So that should have doubled the pressure. So that should have gotten us to 2 atmospheres. And then we made the temperature a lot higher. So we were also bouncing into the container. We made the temperature 750 degrees Kelvin. So more than double the temperature. And then that's what got us to 5 atmospheres. Now, one other thing that you'll probably hear about is the notion of what happens at standard temperature and pressure. Let me delete all of this stuff over here. Standard temperature and pressure. Let me delete all the stuff that I don't need. Standard temperature and pressure. And I'm bringing it up because even though it's called standard temperature and pressure and sometimes called STP, standard temperature and pressure, unfortunately for the world, that they haven't really standardized what the standard pressure and temperature are. Standard temperature and pressure. Temperature and pressure. I went to Wikipedia and I looked it up. And the one that you'll probably see in most physics classes and most standardized tests is standard temperature is 0 degrees Celsius, which is, of course, 273 degrees Kelvin. And standard pressure is 1 atmosphere. And here on Wikipedia, they wrote it as 101,000 or 101.325 kilopascals, or a little more than 101,000 pascals. And of course, a pascal is a Newton per square meter. All of this stuff, the units are really the hardest part to get a hold of. But let's say that we assume that these are all different standard temperatures and pressures based on different standard making bodies, so they can't really agree with each other. But let's say we took this as the definition of standard temperature and pressure. So we're assuming a temperature is equal to 0 degrees Celsius, which is equal to 273 degrees Kelvin. And pressure, we're assuming, is 1 atmosphere, which could also be written as 101.325 or 3/8 kilopascals. So my question is, if I have a gas, if I have an ideal gas at standard temperature and pressure, how many moles of that do I have in 1 liter? How many? No, let me say that the other way. How many liters will 1 mole take up? So let me say that a little bit more. So, and then I also have, so N is equal to 1 mole. So I want to figure out what my volume is. So if I have 1 mole of a gas, I have 6.02 times 10 to the 23 molecules of that gas. It's at standard pressure, 1 atmosphere, and its standard temperature 273 degrees, what is the volume of that gas? So let's apply PV is equal to nRT. nRT. Pressure is 1 atmosphere, but remember we're dealing with atmospheres. 1 atmosphere times volume, that's what we're solving for, I'll do that in purple, is equal to 1 mole, we have 1 mole of the gas, times R times temperature, times 273. Now, this is in Kelvin, this is in moles, and we want our volume, let's say we want our volume in liters. What is that? The VPN, okay. We want our volume in liters. So which version of R should we use? Well, we're dealing with atmospheres. Atmospheres, we want our volume in liters, and of course we have moles in Kelvin, so we'll use this version, 0.082. So, this is 1, so we can ignore the 1 there, the 1 there. So the volume is equal to 0.082 times 273 degrees Kelvin, and that is 0.082 times 273 is equal to 22.4. It's equal to 22.4 liters. So if I have any ideal gas, and all gases don't behave ideally ideal, but if I have an ideal gas and it's at standard temperature, which is at 0 degrees Celsius, or the freezing point of water, which is also 273 degrees Kelvin, and I have a mole of it, and it's at standard pressure, 1 atmosphere, that gas should take up exactly 22.4 liters. And if you wanted to know how many meters cubed it's going to take up, well, you could just say 22.4 liters times, now how many meters cubed are there? So for every 1 meters cubed, you have 1,000 liters. I know that seems like a lot, but it's true. And just think about how big a meter cubed is. So this would be equal to 0.0224 meters cubed if you have something at 1 atmosphere, a mole of it, and at 0 degrees Celsius. Anyway, see, this is actually a useful number to know sometimes. They'll often say, okay, you have 2 moles at standard temperature and pressure. How many liters is it going to take up? Well, 1 mole will take up this many. And so 2 moles at standard temperature and pressure will take up twice as much, because you're just taking PV equals nRT and just doubling everything else is being held constant, or the pressure, everything else is being held constant. So if you double the number of moles, you're going to double the volume it takes up. Or if you halve the number of moles, you're going to halve the volume it takes up. So it's a useful thing to know that in liters at standard temperature and pressure, where standard temperature and pressure is defined at 1 atmosphere and 273 degrees Kelvin, an ideal gas will take up 22.4 liters of volume.